All right, folks, I've got the report. So here we go. Uh, we're not far off from this. So let's say, go back here. Let's put it on the record that this is the frame. So the first step that you can always do is to solve for the unknown reactions. That's always the first step. And remember that this is still a framing system that we call statically indeterminate. So you can always solve for your unknown reaction. Once you can, once you solve your unknown reactions, you can start carrying out the analysis on your frame. Okay. So now I cut the free-body diagram of the first one. You see that the reactions are already there. In order to maintain equilibrium of this free-body diagram, you probably know that you have vertical axial force equal opposite to the pink one, and then you have the horizontal shear equal opposite again to the pink one. But let's take a look at these forces. You see the axial forces, they coincide, means they pass the same point. So it's perfect equilibrium. But for the shear, the pink shear here and the red shear here, they don't pass the same point, which we call they do not coincide, which means they tend to twist the member. So you can see right away, if you feel the equilibrium, that you will need the moment. And can you feel that when you look at the shear here, see, it's a couple, right? This couple gives you the counterclockwise rotation, right? Can you feel it? Can you feel that this couple gives you the counterclockwise rotation? So without any calculation, you know right away that you will probably need clockwise movement to balance this free-body diagram. Simple as that. So from this, we move on to the next free-body diagram of, say, the horizontal member. And at this joint, you need to maintain equilibrium as well. So without further ado, you have the clockwise moment at the joint for the vertical member. So you know you need the moment equal and opposite here, so that your joint remains equilibrium, under equilibrium. So if the moment right here on this vertical member is clockwise, this better be counterclockwise, or some of you say anti-clockwise. But I have grown up with counterclockwise, so I'll stick to that. This better be counterclockwise and equal to that. And in order to maintain equilibrium, this horizontal force here, this one, will become the horizontal force here in the opposite direction. Can you notice the change? What once was the shear force on this member now becomes the axial force on that member. And here you have the vertical downward. So yeah, likewise, you have the vertical upward. Again, what once was the force, the axial force, which is parallel to the member, now becomes a shear force that is perpendicular to the member. And now you may have the external force you can carry out to the opposite end to get another, um, you know, internal forces at another joint. Now, ladies and gentlemen, there's something you should know right away. Let's take a look at the column on the right. See what happens. I'm going to draw a PVD diagram again. Not very nice, but acceptable. Just look at the reaction you have. Because it's a roller, right? So that means you cannot have the horizontal reaction over there. Correct? It's a roller. So the only thing you can have is here. What's the meaning of this? Remember that this is a roller. No horizontal reaction. Correct? Meaning when you try to solve your structure and you arrive at this joint and you have the horizontal force at this joint, what's the meaning of it? Yeah, this column will become unstable. So by taking a look at the system and look at this free body diagram, you know right away that you can never have the horizontal force. And when there is no horizontal force here, this joint better have no moment as well. Otherwise, it becomes imbalanced. Right? So it's pretty simple. Okay. Now, one more thing that I'd like to point out is that some of you can write the free body diagram of two members just like this. But in some cases, it could become a little bit problematic. So, for example, if you have, which is a normal case, if you have the horizontal external load applied. So to write the free body diagram straight away like this may confuse you. Another way is just to try to write the free body diagram of a joint itself, which essentially means we are trying to write the free body diagram of a dot, you know? Can you write the free body diagram of a dot on your beam? Have you tried it? Ah, interesting, right? Let's say if I'll use a different space. If you have a beam, okay, with the load, whatever that is, and cut the free body diagram and say, I want to draw the free body diagram of the dot at that point. What would it be? What would it look like? Say you have a beam here, and then you have a just tiny piece of your structure there, and then another piece. Can you draw it? It will be quite a challenge. Okay, so likewise, I'm gonna draw the free body diagram of this joint, and I don't know if it's been deliberate or not, but are you okay? Okay. But I sort of try to avoid naming the joints, so it becomes very difficult. But that's why we need names, right? We need names so that you can call me without using just explanation. Let people know that you're referring to me. Suppose I don't have a name. You have to try to explain. Oh, that instructor is crazy long hair instead gray. So everybody knows. Oh, that man. Instead of instructor. Okay, everybody knows. So that's an importance of the name. and not go so crazy changing the name because somebody says, "Oh, my name is not good enough. I was born on that day, but I name like this." And blah 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 blah. People miss the point of everything. Anyway, we better start calling our structure with the names, right? Because it's a lot easier. Oh, too much. So let's call that A, B, C, and D. So now, instead of jumping from member AB to member BC right away, I can draw the free body diagram of my joint B. Okay. So FBD of joint B. Now remember, member AB. Okay, the joint should look like this. Okay, it's a bit more like a ridge joint. And remember, you have a clockwise moment at the end of member B. So it better be counterclockwise here. Right? So that when you sum sigma moment at that point, 0. And again, you have the horizontal shear going to the left, so this is going to the right. Remember, this joint actually is just a dot. Essentially, it's just a dot. Okay. And I have the downward axial force here, so this better be up. And this goes up, so this better come down. This goes to the right, so this goes to the left. And this is counterclockwise, so the moment at this side is clockwise. Then again, these three force components will be equal and opposite to all these forces at the end of member BC. You see? Clockwise, counterclockwise. Here the arrow is not very clear. Right? Clockwise, counterclockwise, going to the left, going to the right, going down, going up. So whenever you become confused, especially when you have the presence of the horizontal load like that at the joint, maybe it's not a bad idea to try to draw the free body diagram of the joint itself, or just the dot B. Okay, remember the actual size of this free body diagram is just a dot. But I emphasize it a little bit so that you know the difference between the force component. Okay, so is there any question about this? So essentially, up to this point, we learn the new system called frames, which is the system where you put more than two members together. And many times most of the time, we are required to have the joints that connect the members to be rigid. The meaning of the rigid joint is pretty much like a rigid body, which means at the joint, it should be able to transfer all kinds of components, axial force, shear force, and the bending moment. Okay, and I have emphasized once in the morning that in order for you to proceed and analyze the members, when I say analyze the members, generally I would mean to obtain the shear force and bending moment diagram. In order to do such things, you would have to make sure that all the forces that you use would have to be either parallel or perpendicular to the member. So there will be times when you need to do a little juggling to turn the force into the right axis. Okay, So up to now, is there any question? Piece of cake, right? So let's rock. Okay. Here we go. Oh, that script. I just, pops up in the middle of nowhere. Okay, we have a lot. So let's begin with this one, right? Okay, we have more. Okay, that's it. Let's begin with the easiest one. Okay. Now, we have essentially the same frame, but I just play around with the support condition. Let's try to demonstrate to you what's going to happen. Okay. So again, you see, I think it's your first job to identify the unknown reactions, correct? So I think it's pretty straightforward from this that for both frames, you have 3 unknown reactions, meaning this is, of course, try to write it down to help you. We're still dealing with statically determinate. Structure. And one thing I like to point out before we begin, but I can't because you guys are making notes. Okay. When I like to point out something, it means I want you to know. Okay? I'm not pointing out things when you are at the most vulnerable moment. Okay, you're writing something, and then I try to tell you the most important thing while you're just busy writing. So I give a minute. Okay. I've seen in many years when some students have trouble solving for the reaction to the thing. So let's say with this picture, this way. And let's say I have exactly the same. Okay. Two support at the same location, and this force at exactly the same location. And then I have this frame. Would the reactions change? No. Good. So it doesn't matter what I have in the middle. The reactions is just what makes sure that your system will be held in place. So don't get confused when you have a crazy looking frame, because it doesn't change the reactions as long as you are in static work, right? And I know I go too far to demonstrate the point. I may as well write a box. The reactions will remain the same. I may as well write whatever that is, a pentagon, yeah, and your reactions will remain the same. Now you get the point. Okay. So let's. Seriously, I'm sorry. Didn't expect it to come back. Okay, I just want to get rid of this. So now you know. As long as the system is statically determinate, You should always be able to find the reactions. Don't be scared by the appearance. Okay. Yeah, that's one of the things that students used to talk to me. You can't panic when you see my exam. You need to relax, try to see through the problems. I'm pretty good at spooking students. Yeah. No, I try not to do that anymore. But I guess it's probably in the blood. You know? Okay, so I don't have anything with me. So it means I of course I need your help. But we will do this together. Okay. Let's begin with the first one. Would you prefer blue or dark blue? Blue? Oh, blue is your color. So let's look at this system. You know, are we going to use the superposition again? We don't need it now, but you know, I always do something. Make the calculation look good. Okay. So we have 800 here. I remember some of you guys sent me a message yesterday asking about how to write a reaction on the structure. You know, I know that Ajahn Julapot has taught you to replace the support with the forces, correct? But it's up to you. But I prefer to write both. It comes down to me because if I keep the support conditions, I will always know what I am dealing with. And I will know what's right or what's wrong. Sometimes when you remove the support conditions from your drawing, right, totally, it's hard to track down whether or not you get the right reaction. But anyway, if this is 800, it takes you 1 second to know that this is also 800, correct? Yeah. So when you look at this, what are you trying to write for the book? Are you trying to I have never seen you stop, so I wonder. Is there notes in this part? Really? I didn't know I write that much. So that I could wait, okay? Sometimes I really want you to listen. Don't stop. Finish it. I'll wait. Really? You finished? You finished exactly when I said, please stop writing it. What is oh, just 18. Okay. Maybe she just drawn it. Anyway, you see, everyone can say it's 800, but can you see that this 800 is producing a counterclockwise moment equal to 800 multiplied by 4? Don't write anything. Just okay. Can you see that you are now having the counterclockwise moment? So you would need the clockwise moment to balance it up. And it should be equal. This moment is 800 multiplied by 4, 3,200 kilogram of kilogram force meter. But now you need something that is going to be multiplied by 6. What's that going to be? Gives you 3,200. So, yeah, let's not do it. Because you need the head, so let's not. So essentially, that's the moment we're looking for. But now you need this 3,200 balance system. But you also notice that there is no vertical force applied, meaning that in order to have this, you need to have a couple, right? Otherwise, you can never have the satisfied sigma Fy equal to 0. then you see right away that you have to have the reactions going the opposite way in another couple in the vertical direction. And it has a moment arm of 6 meters. So this basically is 3,200 divided by 6. See, reactions without calculation. When you feel it, you need to say over exert yourself in doing unnecessary things. Right? Everybody has learned about couple, right? But you don't see a couple. It's there, right? It's there. No, feel it. Now we have balance. We have balance with sigma fx. And we know by balance with sigma fx, that the two forces do not coincide, so it creates moment. So we create moment in another direction, balance the entire system. And in doing so, we find out that we also have the vertical reactions. And since we don't have the external vertical load, you know right away that your vertical reactions here must be equal and opposite, balance themselves out. Simple as that. Change, right? Yeah. Water is. All right. So pretty straightforward, right? So we have solved our structure in the first step, meaning we have eliminated the atoms. Now everything is known. It's time to proceed and talk on stop cycle. Anyway, let's look. Okay, before that, gotta give some name, right? So let's call this A and B and C and D. Generally, I give freedom to students to name names, so that it's getting weirder every day, every year. So you may call it by using maybe Greek alphabet, Chinese characters, Egyptian hieroglyphics. A, B, C, D, nice enough. Okay. All right. So now, without further ado, let's take a look at the free body diagram of member A. Okay? Damn it, I use a lot of colors. Okay. 800 is there. I'm miserable. 800 is there. And we have 3,200 over 6 there. So you would know right away that I will try to use different colors, okay, so that you feel that other internal forces come because of equilibrium. Okay, these green and red represent external reactions. Okay, so I will try to use different green. Now you know it has to be equal and opposite over there. So it's 3,200 over 6. Okay. And of course, this will be 800. Now you know the two 800s, they do not coincide, so you better have moment. Otherwise, your member is not balanced. Correct? the two 800s will give you counterclockwise couple. So you would need surely the clockwise move. Okay, and this this clockwise moment was 800 multiplied by 1. It's a cake, right? So far, yeah. It's difficult. It's always easy until you find crazy structure, right? To test your beliefs in equilibrium. A free body diagram. Do you still believe in them? Of course you do. So we can essentially move on to the member. You know what? Let me point out right here, because I use description here. Let's go back here. Determinate frame. Calculate reaction. What's the first step? We have finished. That's 20%. Can obtain proper free body diagram of all members, because I emphasize on equilibrium. So before you start writing your shear force and free body diagram, you have to complete the free body diagram of every member first to show me that you can balance your structure. Always finish the free body diagram first. Give me the proper system. Don't start your diagrams, because your diagrams may be wrong if your free body of all the members are wrong. Okay, so you may want to leave the space here and okay, try to complete the free body diagram. Member BC now. Okay, now you have 800 go left on AB, so this better be 800. Correct? We have the moment is clockwise, so this better be counterclockwise. Have a downward shear. I'm sorry, we have the downward axial force. So right here, better be up. Okay. Again, this member BC doesn't have any external force, so you can go ahead and say I got another color. This better be equal and opposite, right? So it's gonna be 800. Maybe you think I should change color so that you know it's for balance the force. Maybe. Maybe say anything. Maybe. Okay. See if I can find the colors. Now it is the upward shear here, so it better be downward shear down there. What color? I use this one. Probably don't see. customize phrase. That is 3200 over 6. We can easily do that because it's sigma fx and sigma y. There's no other force present. But what about moment? Now it is time to do some calculation. Figure out moment at C. Right? What about moment at, it's not going to be 3200 anymore. If you can recall that the length of the member is 6, you are beginning to see that moment at C is going to be 0. Because again, if you can look further forward, you know that member CD has a roller at D. So in order for member CD to be balanced, you can't have moment C. So before we calculate this, I'm just going to jump forward and try to write the free body diagram of member CD just to show you. Oh, it's not easy to draw the straight line or vertical if you don't use the program field. So we have 3200 over 6 as a reaction. Just that. And now you know right away that this better be 3200 over 6. And that's it. This is the free body diagram of your member CD. You can't have anything else. Anything else that comes in here would mean something that's not equilibrium. So coming from member, you can always start your work, left to right, right to left, start from C, B, C, whatever. Oh, yeah, right, you're right. I'm too can't. Thank you. Be downward, right? It should be upward. Thanks a lot. Like that. So if you begin your work from CD, you know right away that moment at C has to be 0. Can't be anything else. And that's why I emphasize on finishing your free body diagram first. Right? Always finish the free body diagrams, all the diagrams first. Or break. I'll try to go slowly that you can absorb your pace. The question? Can you speak up? I'm all. Want to see this? Are you trying to see what color should do? Just kidding. So now before we go on to break, let me show you but you should see from the number. We're gonna take sigma MC equal to 0. Okay. So you have I'm not sure, but I've seen every year before this that some still struggle with the direction of the moment. You should see that 3200, the purple one, is trying to, doing the counterclockwise rotation. If you take momentum C, and then the 3200 over 6 green here is trying to do the clockwise. So you can just go ahead with the calculation very easily if you can see the direction. So for me, it just becomes, doesn't matter which one you set positive. So it's 3200 minus 3200 over 6, which is a shear, right? But then, the height, the length of the member is 6. So essentially, that becomes 0. And you should know, always trust equilibrium. If it doesn't come down 0 here, you must find what's wrong with it. Don't say, oh, it's correct. Fine. Go ahead and put moment on member CD. That would really make me very, very upset, to say the least. Because you don't believe in equilibrium. Right? So that proves that 0. But that is your correct free diagram. But now, okay, time is up, and I think it's nice that we can have a break now. Right here, I will come back in the next break to show you the free body diagram, because nobody wonders why we have 800 here. It's not here anymore. Where did it go? Okay, all right. Until the next break, 15 minutes.